So far we have seen several variants of CNN architectures, which firstly tried to increase the depth to improve performance, then tried to make computations more efficient while not sacrificing performance, and then finally variants in which it was okay to sacrifice performance, but you needed to bring the CNN under a lower regime of computations. We saw all of these variants, and in all of these variants, including the squeeze excitation network, the backpropagation of the CNN by itself was not affected, which let us play with these architectures. In this lecture, we'll talk about an important aspect of CNNs that allows us with designing architectures for newer tasks or newer domains given an architecture that works on a particular domain. For example, if we know AlexNet works on the ImageNet dataset, how can we leverage that knowledge to develop a model for another domain for another task also? To discuss this, let's start with limitations of CNNs themselves. CNNs have a few fundamental problems. Firstly, optimization of the weights or parameters in these deep models, CNNs are typically deep models, is generally hard. It requires proper weight initialization. It requires a lot of hyperparameter tuning, various kinds of hyperparameters. That's one of the fundamental limitations. Secondly, it can suffer from overfitting because data samples used for training are generally much lesser in number to the parameters being trained. We already saw that AlexNet has 60 million parameters, VGG has 138 million, Inception V1, which is the first version of GoogleNet, had 5 million parameters. An improved version of it called Inception V3 had 23 million parameters. ResNet 50 had 25 million parameters, and so on. So CNNs fundamentally require a long time and a lot of computational power to train these networks. AlexNet, as we said, took about a week to train on 2 NVIDIA GTX 580 GPUs. VGG took 2 to 3 weeks on 4 NVIDIA Titan Black GPUs. And Inception V1 or GoogleNet version 1 took about a week on hardware that was not shared. So all this can become even more difficult when you have to design an architecture for a new domain. In which case, you have to design an architecture, run it for about a week or several days, see how it works, go back and change a hyperparameter, again run it for one more week, see how it works. And this kind of an approach to designing new architectures or CNN architectures will not scale. So how do we manage doing this for newer tasks and newer domains? Some things you can try is perhaps try good weight initializations. So that way you become independent of the design of the architecture. We've seen Glorot or He initialization. That's one possibility. You can also initialize your CNNs with hand designed filters. You could use an edge filter or one of those filters to initialize the filters in convolutional layers and then ask the CNN to fine tune them. Or we've already seen unsupervised greedy layer-wise pre-training as another approach that could provide an initialization which the neural network can then capitalize on. As we said earlier, this approach of unsupervised greedy layer-wise pre-training is not used these days due to the increased computational power and also dataset sizes. It takes a long time to do the greedy layer-wise pre-training as only an initialization method. The other thing that we talked about to improve training of neural networks is to use regularization methods, be it L2 weight decay, L1 weight decay, dropout, batch norm, adding input noise, adding gradient noise, data augmentation, so on and so forth. This may alleviate overfitting, but may not really lead to faster training of CNNs. So what do we do? An interesting property of CNNs, which has been observed, which is something that we'll focus on in the next week of lectures, is that if you visualize the filters that are learned by layers in the convolutional network after training the CNN, one happens to observe that the earlier layers have filters that probably represent filters that could capture oriented edges of different kinds, color blobs, so on and so forth. In other words, these are what we call low-level features, simple low-level features that we get out of images. Filters that are learned by intermediate layers in a CNN seem to capture some mid-level features which could be considered as combinations of low-level features. A certain texture that's a combination of two edges, or a certain congregation of colors and edges in colors, and so on and so forth. And finally, the filters at later layers learn high-level features such as impressions of objects, for instance, which are higher level abstractions when you compare to only edges in the initial layers. The question we ask now is, what can we do with this? Can we use this in some way? Can we use this understanding of how CNN filters are learning to be able to design architectures better for newer tasks and newer domains? The answer there is a setting in machine learning known as transfer learning. In transfer learning, before we go to transfer learning, in traditional machine learning, if one had different tasks, you would have a data set for each of these tasks. And using a data set for each task, you would have a different model through a learning system that you learn. In transfer learning, you have a set of source tasks that are given to you and a target task on which you want to perform well. That's the new domain, a new task that you want to solve the problem on. So when we say source and target, for example, you could imagine now that you have trained AlexNet on the ImageNet dataset, and tomorrow you have data coming from a different domain. For example, let's say you want to build a recognition of objects for self-driving cars in India. These objects may be different from the objects in ImageNet. So how do you now transfer the model that you learned on ImageNet to a model that you want to develop on in a new domain? In this case, you try to use the data in the target domain as well as the model or the knowledge that you got from the source domain to be able to learn a model for the target domain. So this we call as transfer learning, to be able to transfer knowledge from an earlier source task to a target task that we are currently interested in. How does this relate to the hierarchical learning of abstractions of features in CNNs? We'll see that in a moment. So we know now that using knowledge learned over a different task to aid the training of current task is transfer learning. We now also know that we do have pre-trained models with good results available to us. For example, an AlexNet on ImageNet is pre-trained and that model is already given to us. Can we leverage this in some way to improve performance on a target task? We can do this in a couple of ways. We can do this because we know that the AlexNet's filters or any other model's filters, any other CNN model's filters for that matter, has some general features in the first few layers, and the features slowly start getting specialized as you go to deeper layers. Why do we say that? If you go back to an earlier slide, you see that the earlier layers filters seem to capture general information like edges and color blobs and so on, whereas the later filters seem to capture some object-specific information which could be specialized for that task. So what we can do now is you could take a pre-trained neural network such as an AlexNet to a newer domain and keep all of those weights of AlexNet exactly the same. Don't update them for this new task. Instead, take only the last layer, which we call as the classification layer, and train only those parameters for the newer task. We call this to be fine-tuning, where you are initializing the weights of a network for a new task based on some pre-trained weights of another model, and you only fine tune certain layers in the new network for the new task. You could now, we talked about the first setting here, which only trains the classification layer. You could also use the pre-trained weights as an initialization and then fine tune the entire network or certain layers at the end of the CNN, not just the classification layer. You could take the last 3 layers or last 4 layers, anything of your choice, to fine tune to better model the target task. Which one do you choose? Depends on your dataset size and how similar is your target task to the source task. Let's see a few possibilities here and see what we can do. If your dataset was fundamentally small and your target and source datasets are fairly similar to each other, what you can do now is, because this target and source datasets are similar to each other, you could say that the specialized features are likely to remain the same in both these datasets, right, for models trained on both these datasets. So what you can do now is you take the source tasks generic layers, you take the source tasks special layers. So this entire block that you see in the middle could be an entire pre-trained network, such as an AlexNet or ResNet that you trained on another dataset, which we call as a source task. We leave that as it is, and we only train, you randomly initialize the classification layer alone and train only that one for the outputs in your new task. This is because your dataset is small, you feel you may not have enough data to retrain or fine tune all these feature extraction layers. Let's as well focus only on training the classification layer properly. So in this case, we are initializing the new network with a pre-trained weights, and we are fine-tuning only the classification layer. Another setting is where the dataset is small and also the target and the source datasets are dissimilar this time, which means the specialized features, the general features could still be common. The edge detectors and those kinds of filters could be common for the source and target task, but the specialized features may not really be common between the two tasks. What can we do here? We now consider the entire pre-trained CNN, because we know that the feature maps of the generic layers, which are, by general layers we mean the early layers of the CNN, you can consider that from your pre-trained network, take those feature maps as output, and then train another classifier such as support vector machine, or could also be a neural network, to give you the output for the target task. Why are we doing this? Because the dataset is small and the target and source datasets are dissimilar, we cannot use the specialized features of your pre-trained network on the source task. We now assume that the generic features that we get from the first few layers, by features, by representations, we mean those feature maps for each input. Those generic representations we assume will help us improve performance on a classifier, although the dataset is small. A third setting now is when your dataset is fundamentally large. When your dataset is large, you have some more luxury. You can now use the pre-trained network as a good initialization to fine-tune the entire network now on the target dataset. But you can do a couple of things also intelligently to improve performance. While fine-tuning, you can keep the learning rate to be quite low. Remember, learning rate is the coefficient of your gradient in your gradient descent method. You can keep your learning rate to be quite low so that your pre-trained parameters are not changed significantly. You are saying that I still want my overall network weights to be similar to the weights that I learned from my source task. But I have the data, I'm going to update it, but let me keep the learning rate low so that I don't make too many updates to my weights from what they were from a source task. On the other hand, if dataset is very different and the dataset is large, there are explicit methods for this, such as what is known as transitive transfer learning or things like that, where you can either train from scratch You don't need to fine tune at all. You can randomly initialize using Glorot's initialization and train from scratch on the new target task, because you have a large data set. You're saying that the target task and the source task are not similar to each other. So you may as well train from scratch or use methods such as transitive transfer learning, which is a known method in traditional machine learning, and that can help you improve performance here. The main idea of this discussion is to tell you that the design of architectures for CNNs, while we saw a few different designs, it's not trivial to design newer and newer architectures for a given problem. There are many hyperparameters, number of layers, width, resolution, number of filters, also learning hyperparameters. To try to come up with the appropriate combination for a domain and a task by itself can be a very difficult task, and using the idea of transfer learning and fine-tuning could help you take an existing architecture that has solved a different problem and adapt it to a new problem. This is a very common procedure that people follow to take CNNs to newer domains and newer tasks. For more reading, you can read chapter 9 of the deep learning book and the lecture on transfer learning in CS 231N. And if you're interested, one of the earliest articles that tried to study how transferable are features of CNNs in the context that we just discussed.